So yesterday we worked on imaginary numbers. Imaginary numbers, if you didn't get the whole point of yesterday, the whole point of yesterday was basically identify that the square root of -1 equals what? Equals I. And then we extended that further, and we said I squared equals -1. Feel free to talk at me. And then we found out I cubed is a -I to the fourth is 1, and then they spiral back and forth, right? Well, today what we're talking about is we're talking about the complex number system, which includes imaginary numbers in it. Okay, there's some confusing pieces and parts of today. So what we're doing is we're talking about the set of imaginary numbers yesterday, and everybody's going to ask why this is, I'm assuming, but all imaginary numbers can be written in the form of a plus bi. Now this is important to see. This is a standard form. You have an imaginary number. It has to be written in this form. And if it's not written in this form, it's wrong. Okay? And a and b, that b there, they are real numbers. And if it's an imaginary number, b cannot equal 0. Because if b equals 0, my whole I would be gone, right? And I would be just left with the a part. And if the I is gone, the whole imaginary part of the number is gone. Then they talk about a pure imaginary number. A pure imaginary number is an imaginary number in the form of bi. Well, that means a is 0, right? No big deal. It just has an imaginary part, and that's it. Okay? So we want to take the number I, the imaginary number I, and we want to write it as a complex number. This is a doozy. How do I write I as a complex number in the form of a plus bi so I can identify what a is and what b is? Anyone? No one. No one wants to talk. No one wants to be recorded. Okay. 0 plus, technically 1, that's a fancy one by the way, I. That is in the form of a plus bi. What is a? Well, a obviously would be 0, and b, hopefully obviously, would be 1, a fancy 1. And I can see the coefficient on I is 1. So I'm going to ask somebody in here to give me an example of a pure imaginary number. Anyone you want, I don't care. There's an infinite number of them. Give me an example of a pure imaginary number, sir.
1 billion I.
1 billion I. I like it. How many zeros are on that? Too many. That is a nasty, disgusting, dirty imaginary number, but that is a pure imaginary number because a is not there. Okay? Question of the day is, can a number, now what they are talking about here, I want to clarify, can a number, they're talking about a complex number, a plus bi, can a complex number be both a real number and an imaginary number? Is that possible? Cole says no. Why not, Cole?
Well, a real number means it can be plotted on a graph. Like, imaginary just means like it's the square root of a negative value. It can't be represented as a regular constant.
It can't be represented as a regular constant in the real coordinate plane, but there is such thing called an imaginary coordinate plane. They have their whole system of numbers. But you're right, no they can't. Why not? If a equals 0, if my a is 0, what kind of number is this? It's imaginary, right? If a equals 0, it's imaginary. If b equals 0, what kind of number is it? It's a real number, right? Because your i's gone, so if b is 0, it's real. It's a real number. And if A and B both are non-equal to 0, what kind of number is it? It's an imaginary number because i's in it. Okay? Now we just got talking about up here, imaginary numbers are in the form of a plus bi. So now we got to come down here, we're going to talk about imaginary numbers within the set of complex numbers. Complex numbers have the same definition. They are in the form of a plus bi, where a and b are both real numbers. Okay? B would be multiplied times I. A real number times I is an imaginary number. Okay? And the term A, right here, your A is the real part of the complex number, and the BI is the imaginary part of the complex number. Okay? And this is important to understand because now we have a whole new classification of numbers. There's a whole new classification coming with us today now. And in order to see this classification, let's talk about all the numbers real quick and short and sweet that you've dealt with up to this point in your mathematical careers. And we're going to make like a little hierarchy chart, if we can call it that, a diagram to show the relationship between each set of numbers shown. So you have talked about in your math career, you've talked about complex numbers very briefly now. Imaginary numbers very briefly now. You've talked about integers since the elementary school. Irrational numbers since probably about 6th or 7th grade. Natural numbers, elementary. Rational numbers since the day you started math, kind of. Real numbers, same thing. Whole numbers, same thing since you started math. So we're going to create a hierarchy chart. And on the top, we now are going to be looking complex numbers. I checked off my complex numbers. What are the two categories that will fall underneath complex numbers? Well, a complex number has two parts of numbers, doesn't it? It has a real part and an imaginary part. So, we are going to have two categories. We are going to have real numbers, and we are going to have imaginary numbers. Okay? Imaginary numbers and real numbers. Now let me ask you, any of these other definitions, integers, irrational, natural, rational, whole numbers, if we talked about those previous to now, can they fall underneath the imaginary category? Hopefully, obviously not. So all these other categories fall underneath real numbers. What are my main two categories underneath real numbers? You guys are even more dead today than normal. What are my two categories underneath real numbers?
Rational and irrational.
Thank you. Rational and irrational. Awesome. So we have irrational numbers, and we have rational numbers. Okay? I don't know if you remember the difference between irrational and rational. Irrational numbers, okay, those are numbers like the square root of 3. Those are numbers that, how I always think of them, they never repeat, they never terminate, and they go on and on and on and on and on forever like I have been so far today. They never quit, they just keep going. They are irrational. Rational numbers are any numbers that can be expressed as a fraction where the numerator and the denominator are both integers. So, 2. 2 is a rational number because it can be expressed as 1. 2 over 1. Okay? Underneath my rational numbers, we have some other classifications. Underneath rational numbers, we will have integers. Integers are the numbers. Basically, they stop, say -2, -1, 0, 1, 2, and they go on and on. Okay? No fractions, no decimals, those are integers. No fractions, no decimals, integers. Integers include positive and negatives. From integers, we talk about whole numbers. Right? Check my integers off. We're going to talk about whole numbers. Well, what the heck are whole numbers? Whole numbers are part of the integer group. Whole numbers are numbers, basically, they start at 0, 1, 2, and they go on, and they include, including 0, they hold all the positive integers. And the very last one is natural numbers. This is nat numbers. Natural numbers, basically, they're a lot like whole numbers. Some textbooks define them as not including 0 and just the positive integers going up. So that's really mainly the separation category between whole and natural. Some say they include 0, some say they don't. Kind of same category. The only reason why we're looking at all the classifications of numbers is because when we start solving equations, we're going to be talking about imaginary numbers and real numbers, okay? And notice, imaginary and real both fall underneath the complex category, so they can be the same sometimes. A real number can be an imaginary number. Or, I'm sorry, a real number can be a complex number. And an imaginary number can also be a complex number. So that's why we're talking about the classifications of them. So here we go. Here's a hard one. This is going to blow your mind. Trust me, we're going to do operations with complex numbers, and it is crazy hard. So let me parallel right above here in A. Let's look at this. Let's say we had 3 plus 2x minus 1 minus 6x. Let's say I looked at it and said, I don't like imaginary numbers. I want to deal with them. How would we have subtracted these up here? What do you do to them? Somebody's got it. I need some help. Come on, come on. How do we subtract them? What do you think? Kylie. These up here. You know how to subtract them. How do I subtract the top? 3 plus 2x minus 1 minus 6x. Yeah. You're just going to look at it and say 3 plus 2x. You're going to picture that distributing minus 1 plus 6x. You're going to combine your like terms. You're going to get 8x plus 2. No questions asked. You can't put the 8x and the 2 together because they're not like terms, right? Complex numbers, guess what? They kind of work the same way. I'm going to interpret this I like an x. It's not. Okay, it's square root of -1. But I'm going to look at it like a variable. So I'm going to say 3 plus 2i minus 1 plus 6i. And when I'm simplifying expressions with imaginaries, I have to understand and remember a plus bi form. Doesn't have to be in parentheses, but the real part is always unconditionally written first. So I'm going to say 3 minus 1, that equals 2. And then I'm going to put my imaginary portions together, plus 8i, and that is what they are when they put them together. I just combine like terms the same way I always did. Now when I look at C, skipping B because of that wicked fraction in there. Now, how am I going to take 5i times 3 minus 2i? The same stinking way you always multiplied stuff, okay? What is 5i times 3? It is 15i, right? What is 5i times negative 2i? It is negative what? 10i squared. Now when I'm multiplying, my powers of I are changing. So now I need to look at this really as 15I minus 10. Now, we remembered yesterday, I squared is really negative 1. So we're really looking at 15I plus 10, aren't we? And is 15I plus 10 in my A plus BI form? No, I just need to reverse the order in which they are written. It is important that I do call it 10 plus 15I. Now it's a complex number. And the confusing part of a complex number is this is a number, this whole thing. It's one number. It's not two, even with the addition between it. It's one thing. It's one complex number. Okay? How about the bottom one there, D? Same thing. I'm going to multiply. Outers are going to come minus 15I plus 6I. And then I'll say minus 9I squared. I'm going to quickly combine my like terms that I see. And I'm going to come across, I'm going to call it 10. I'm going to combine those guys, minus 9I. And then I say minus 9. And I say, oh crumb, there's an I squared that's really a negative 1. And you're probably not going to show the work the way I'm showing it right now. You're probably going to quit writing this. And you're probably going to jump from here. You're probably going to bypass pretty quick and call it 10 minus 9I plus 9. Because that times that, multiply those two, gives you positive 9. Then you have another set of like terms that'll get jarred together. 19 minus 9I, and now it's a singular complex number. Okay? Now I want you guys to take a couple minutes here. It shouldn't take you any more than 2 to multiply A, C, and D in number 2. Multiply them up. So to multiply these, there's something very special going on in all three of these that you have to identify to make your life easy. Okay? 2 times 2 is 4. 2 times negative I is negative 2I. I times 2 is plus 2I. I times negative I is negative I squared. Oh, look at that. When I put my like terms in the middle, these outer and inner terms, they kill each other off. So when I look at this, I'm really looking at 4 plus 1. Is it okay if I write 4 plus 1? Because I know this I squared is a negative 1, and a negative 1 is a plus 1. Did you get 5 for A? Okay? Then C. I'm going to multiply C. 3 times 3 is 9. And then I get a minus 6I. And then I get a plus 6I. And I get a plus, nope, I don't get a plus, I get a minus. I get a more, oh boy. I get a minus, and I get my 6I. I get a minus 4I squared. And look at that. Those middle terms killed each other off again. And is it okay if I look at this and call it 9 plus 4 now? Because in the end, I know that's negative 1. And all negative 1 does to a term is change its sign to get 13. Did you get 13 for that one? What did you get for letter D? Somebody give me what you got for D. Anybody get one? 10. Did anybody else get 10? Answer there is 10. You're going to multiply it the same exact way. What do you notice about all three of these that we did? This is critical. What do you notice about them? Are the two things I'm multiplying very closely related? Yay or nay? They are incredibly closely related, aren't they? They are called complex conjugates. In any time, complex conjugates are, notice the A in the A are exactly the same. BI and BI are exactly the same. The only thing that is different is the sign between the A and the BI. Otherwise, they are identical matches. You use complex conjugates, you use conjugate pairs in all levels of math, whether you're in complex numbers, if you're in square roots, to rationalize the denominator, okay? We use complex conjugates. What also did you notice coming into this next slide? When you multiplied all three of those, when you multiplied those complex conjugates, what did you notice? You noticed their product was always a real number. And further than that, because when I actually take this one times this one, if I look at my outside and my inside terms, they always kill each other off. So the second I see it as a complex conjugate, all I need to do is take A and square it, take B and square it, put them together to get my numbers. It's a shortcut once you identify these things, okay? Now we're talking about, even further, polynomial. Remember that a polynomial in mathematical expression is involving the sum of powers in one or more variables multiplied by a coefficient. Okay, that's a whole mouthful of garbage, right? Bottom line, we're talking about the definition of a polynomial. It's a whole string of powers of x, powers of y, whatever, okay? In the end, when you were in Algebra 1, we classified polynomials lots of different ways, but we classified them as a monomial, one term. We classified them as a binomial because they had two terms. We classified them as a trinomial when they had three terms. Trinomials are the ones we factor all the time. And anything above three terms was called blanket polynomials. Okay? We're going to extend these definitions. We're going to identify monomials, binomials, and trinomials into complex numbers, whether they're real or imaginary, because they include both of them. This is confusing. You got to wrap your mind around this. It's kind of goofy. So we're coming down here to number 3, and we're looking at Maria. Maria says that the expression of 3x plus xi minus 5, she's calling that a trinomial because it has three terms. It has 1, 2, 3 terms. Remember, terms are separated by addition and subtraction. Then we come underneath here and Dante says, well, that expression, no it's not, it's a binomial. Because I can rewrite it into an equivalent expression of 3 plus I times x minus 5. And now I am seeing two terms. I am seeing this first term here, and I'm seeing the second term here separated by a subtraction. Then we got Jermaine. Jermaine says you're both whacked. It's not a polynomial at all, and I believe he's saying that because it's an imaginary number. And who's right? Who do you think's right? Nobody ever wants to answer because they don't want to be wrong. I've been wrong 4 or 5 times already today. I've only been in school an hour and a half. Dante's the genius. Dante's right. Because when I look at this as, and I'll show you exactly what Dante did. Let me get my eraser quick and get that business off. What Dante did is he said, when I have 3x plus xi minus 5, he said, hey, these two terms alone have a common factor of an x in them. So I can retract that x off of both of those. And if I pull the x off the 3x, I got a 3. If I pull an x off the xi, I get plus an I minus 5. And Dante's 100% right. This is a binomial because this is one term and this is one term. And the reason why most people don't want to see this as one term, 3 plus I is A, it's singular, it's A, one complex number times X. So if I take it out of the complex numbers, you're really kind of looking at something that looks like 2x minus 5. You'd call that a binomial all day long because there's two terms. This 3 plus I is probably the most disgusting coefficient you've ever seen in your life to this point, but it's just like looking at a 2 because it's a number, okay? So what we're going to do is we're going to come down here and I'm going to ask somebody, and if I just got to grab my chair and call on somebody, I just want to identify these four things, okay, A, B, C, and D. We're going to classify them quickly, classify them as a monomial, a binomial, or a trinomial. And if it's not one of those, we're going to call it other. Tried to do a different one on each one. Not very good at that. Look at A. What is A? Mono, bino, or trino? I'm getting my chart because I'm still learning. I'm a slow learner. I'm going to start calling on people. What do you got?
Binomial.
It's a binomial, Niemeyer, right?
Yeah.
What makes you say binomial? You see two terms, right?
Yeah.
Okay. My question to you is it in the form of A plus BI?
Yes.
It is. Because it's in that form, it is one number. It is a monomial. Because in the complex number system, that is one thing. And it's really hard to get past that and see that. It's one number. Hey, there we go. Thank you for your participation. You didn't shrivel up and die either, did you? No, he's still here. Everybody see that? Bobby's still here. How about B? Mono, bino, or trino? This is going to be Rachel's. What do you think, Rach? Trinomial. Could you explain where you're seeing your trinomial? Last class said trinomial as well. Are you seeing that as one?
Yeah, and then the next.
That is one. And you're kind of grouping that as one like we grouped over here, right?
Yeah.
Awesome. That's exactly what the last class said. It's close, but this is a binomial. This is a binomial because do you see these first two have that common factor of an x? So I could theoretically retract that x off, look at it as a negative 4i plus 2, a really gross coefficient, minus 5i plus 1, I really don't like it. I want to write it 2 minus 4i times x minus 1 plus 5i. One complex number times x, two total terms, binomial. Thank you for your participation, dear. Much appreciated. Okay, how about C? What do you think, Elke? Mono, bino, or trino? Let's go with binomial. Okay? You're seeing one term, you're seeing one term, right? Yeah. Now, do these two have anything in common that we might be able to turn on the vacuum, suck it out, and factor it off? And look at a complex coefficient tag to it? Pick it up when I'm putting down? Okay, because we have our x squared They each got an x squared. So if I retracted out that x squared, and I'm just going to leave it in front because I'm going to be left with a coefficient, well, that's going to give me 3/2 minus 1/4 I. That gives me a complex number times some power of x mono. And let me tell you, don't feel bad. When I was in your shoes, I never saw this until I saw it for about the 10th time. Okay? All it's doing is it's teaching you, it's trying to get you to see that a complex number is one thing. And I can look at the whole complex number as a coefficient on a variable to see, rather than two things, it's really one. How about the last one? Mono, bino, or trino. Here. Oh, wrong one. No, I did it wrong. We are. Yeah. It's Pratt, right? Nope, I got the wrong one. Help me out. You're not on my stuff. No wonder. So what are we? Hey, you're not on my list. I don't know why. What are you thinking? Binomial. Why are you saying binomial? Separate these for me. Can I rearrange these in any way, shape, or form and take one thing out of two of them to look at a complex coefficient? Picking up what I'm putting down? For instance, is that the same as that? So even if I threw those together, I'm still going to have an x tagged inside of what I got over here, right? Then it's not a complex number if there's an x tagged with it. This is going to be it's a trinomial. One term, one term, one term. Powers of x are different here. Powers of x were the same over here. That's why I could factor them out. Yes, sir. Well, you couldn't do that because if you suck the I off, okay, you paired these two, right? And if you said 3 plus 0.5x squared times I, this is, because there's a variable stuck inside that coefficient, it's not really a coefficient. Does that make sense? Okay. Good shot, though. Good try. So now we're coming down. We're trying to round the corner. I want to give you guys a couple minutes. Look at how hot again. Okay. Take 5 minutes to do these problems quick. We are back online. So as you're simplifying these, I'm thinking everybody's identifying those as like terms, and I got 2 xi's. And hopefully we're identifying xi and xy are not like terms. This is done. Now, when I look at C, I'm real OCD about how I put my like terms together. I always look for the highest powers of x first. So what I would do is I'd come through and I would grab my x's. Just my plain x's. And I would say that gives me 1.5 x's, right? Now the next thing is I'd see a pesky xi in here. So the next thing is I would find all of my xi's. Is that my only xi? So then I would say minus xi. Now I don't have any more x's left. I default to collect my i's. There's a 3i. There's a 1.8i. That gives me 4.8 i's. and my rogue plus 9. Simplify simply means collect like terms. I don't need to separate and see the coefficients on them like we did before. Simplify just means collect like terms. Be done there. Last one I want to do here quickly is D, because there's still lots of issues multiplying things like D. This is 100% not x squared plus 9i squared. It is not that. Okay? We need to remember what the definition of squaring something is. It's x plus 3i times x plus 3i. So it's x squared plus 3xi plus 3 more xi's plus 9i squareds, which will give you an x squared plus 6xi. What are you going to call the plus 9i squared? Minus 9. Awesome. You just jump right to that. You don't have to show that times negative 1. And then you're like, oh, crumb. I don't have any more like terms. I'm done. That one's a trinomial. Okay? E I'm going to skip. Is that okay? We've done quite a few of those already. When typically, yes sir.
For G, would it be negative 9i squared?
Here? No, because what we're doing is when we have our plus 9i squared, okay? I squared, as we're saying, our plus 9 stays there. Mentally, your I squared is negative 1. So in the end, we have a positive 9 times a negative 1, which changes to a negative 9 then. All I does in the end, whatever I is tagged to, I squared, not I, whatever I squared is tagged to, it simply goes away and changes the sign of the term that's right now. That's the most easiest, simplest way to think about it. Okay? So here we go. There are a couple slippery techniques in here that you all, as upper level math students, are going to need to know, or you are going to get buried in calculus. Buried in algebra in calculus, let me put it that way. There are some tricks that you learn early and you start to apply and you master them. But we're just going to bomb through here, okay? We're going to analyze two methods. And we're going to look at these and we're going to say, which two is more efficient? Okay? Because one is always easier than the other. When I'm looking at, is that Shania? Shania? I don't know. Shania? I don't know. My pronunciation is terrible. But she's taken 2 minus I times 1 plus 2i times 2 plus I. And she's pretty smart. Let me tell you the truth. She's pretty smart because she's looking in and she says, hey, I have a pair of complex conjugates here. So if I rearrange these, because 1 times 2 times 3 is the exact same as 1 times 3 times 2, when it's all multiplication, I can rearrange it. I'm going to multiply these conjugates really quick because I know whenever I multiply those, I got a real number every time. So she took her 2 times 2 for her 4, plus 2i minus 2i. They died. She got her minus I squared. She said, oh, that's really 4 minus negative 1. So that whole, when I multiply those, it's just 5. And then she took that 5 times her 1 plus 2i to come to a real quick 5 plus 10i. Where Lindsay down here in the bottom, Lindsay's a very process-orientated individual, and that's fine. Nothing wrong with that. She's like, nope. They gave them to me this way. I'm multiplying them from left to right via the order of operations. So she took that one times that one first, and she left the 2 plus I alone. She simplified all this down to another binomial. Then she multiplied it times her 2 plus 1. Got another trinomial. Took care of her I squared and got 5 plus 10i. Efficiency, I'm going to tell you what. If you ever see and you're multiplying complex conjugates, those are the first ones you want to do because they turn into real numbers. And then you're distributing one thing rather than two things, and it's a lot less math. Okay? You always want to look for complex conjugates if you can multiply them. The next one is getting into the tricks of the trade. To be honest, I never ever did it until I saw it. When I saw it, I grabbed onto it, and I'm like, man, this is the best thing since sliced bread. But Elijah's taken these two terms, multiplying them to this. He's taken these two terms, he's multiplying them like this. And then he's, from back here, he's just combining like terms and putting it all together. Aiden is he is a sharp tack. Or she. I don't know. Had both. Female and male Aidens. Aiden looked at this and said, I have x plus I times x plus 3 plus x plus 3i times x plus 3. Aiden says, hey, there's a common factor of x plus 3 here. I'm going to factor that x plus 3 out. So he retracted that x plus 3 out, set as parenthesis, divided each one of these terms by his x plus 3. Gone, left with the x plus I. Did the same thing here. Gone, left with the x plus 3i. Now, inside the second set of parentheses, you're able to combine like terms. And then you're multiplying two binomials to get a polynomial in this case. This factoring out a binomial, a whole expression from other things, is abstract, but the further you go, let me tell you how much, if you don't master that, you will not be able to simplify some of your stuff in calculus, period. Because you're going to get polynomials that are way too high, you won't have any clue how to do it. So you keep them small, and you factor out bigger parts. But I'd have never done that until I saw it. I'll be honest, lots of things I wouldn't have done until I saw it. I would have you try these with the technique you like on your own later. I'm not going to waste time because we're down to 5 minutes left. And we got to come into here. What is my complex conjugate? We took a lap here now. What is my complex conjugate to 7 plus I? What is my complex conjugate to 7 plus I? What is my conjugate to that? 7 minus I. Complex conjugate, 7 minus I. Okay? What is my conjugate to negative 5 minus 3i? Yep, it is same, opposite, same. It's all you got to do to write a complex conjugate. C is going to be 12 minus 11i. D, ooh, there's a toughie. What's my complex conjugate to negative 4i? Let me help you.
Is it 2 divided by negative 2?
Nope, let me help you. You'll get it. Let me show you the full complex number. Let me write it as a complex number. What's my complex conjugate to 0 minus 4i?
4i.
0, technically 0 plus 4i, but we never write the zeros, so my complex conjugate here is 4i. It's just the opposite sign of it. Okay? So here we go. I don't have much time to explain this. I got just as much time as I had in the last class. Let me relate this to something you've done before. When, and I'll relate it down here, when you had, let's say 2 divided by 1 minus the square root of 3. Do you remember simplifying those where you had to rationalize the denominator? Because fractions are never simplified if there's a square root in the denominator. You remember how you got that square root out of the denominator when there was a plus or minus down there? Remember how you did that? I'll tell you how you did that. You used its conjugate. You multiplied this thing times a1 plus the square root of 3, because when my roots are involved and I multiply conjugates, it eliminates my square root. But we have to do to the top what we do to the bottom, or we change the value of the fraction, which we don't want. Okay? Here's your first introduction to a conjugate back in Algebra 1. You saw conjugates here. We're extending the conjugate to imaginary numbers. Ultimate goal is to get I out of the denominator, in a nutshell. Okay? We're going to multiply by its conjugate over minus 2i. Okay? Now I'm going to multiply this really fast so you got one example to follow in your homework. The numerator, I'm going to expand out. I'm going to have 6 minus 4i minus 3i plus 2i squared. That's going to be over when I multiply the denominator. I'm going to have 9 minus 6i plus 6i minus 4i squared. I know with this conjugate, this is going to be a real number in the bottom. Now I'm going to come to the top. I'm going to collect my like terms. I'm going to have 6 minus 7i minus 2, because that I squared is going to change my sign because it's a negative 1. Then I'm going to have on the bottom a 9, die. That minus 4i squared turns to a what? Plus 4. Still got more like terms I can put together in the top. I get 4 minus 7i over 13. And I'm just going to ask, is that in that form? No, it's not, right? So all I got to do is I got to come back and I'm going to separate it. I'm going to take the real portion, the sign that's between, and then I'm going to take the imaginary spot. Now it's in the form of a plus bi. That's all you're doing, is you're multiplying the fractions by their conjugate. And then have fun with the math.